Hi, welcome to the Olympiad geometry. Let's continue our study of the Ceva theorem. Today we're going to look at a problem that is very classic, and it has lots of variants, and we will talk about these variants in the following videos. So, let triangle ABC be an acute triangle. AD is the altitude on side BC. H is any point on AD. Extension of BH and CH intersect AC, AB on point E and F, respectively. Prove angle EDH equals to angle FDH. There are different ways to do this provement. So I would use a way that's very straightforward and then use a way that you need to add some auxiliary lines. At very first, when we get this figure, we can see that three lines AD, BE, CF are concurrent on point H, which means we can use the Ceva theorem on this triangle and the point H. So let's do that. Use Ceva's theorem on triangle ABC and point H. So we got AF divided by BF or FB times BD divided by DC times CE divided by EA equals to 1. And notice that we want to prove angle EDH equals to angle FDH. So we can just set angle EDH as alpha and FDH as beta, right? Let angle EDH equals to alpha. Let angle FDH equals to beta. So we just want to prove alpha equals to beta, right? That's our target. And from the Ceva theorem equation, we got AF to FB ratio. So the ratio AF to FB can be translated to the area ratio of the triangle ADF and triangle FDB. Once we translate it to the area ratio, then we can include the angle beta into it, right? So AF divided by BF equals to the area of triangle ADF divided by the area of triangle BDF, which equals to half of AD times DF times sine beta divided by half of FD times BD times sine half pi minus beta, right? So that equals to AD divided by BD times sine beta divided by cosine beta. And we have BD to DC here, and we have CE to EA. So look at CE to EA. The ratio of CE to EA can be translated to the area ratio of triangle CDE and the area ratio of triangle EDA. So that equals to half times DC times DE times cosine alpha divided by half times DE times AD times sine alpha equals to DC to AD cosine alpha to sine alpha, right? So if we do the production of these three terms, then we got AD divided by BD times sine beta divided by cosine beta times BD to DC times DC to AD times cosine alpha to sine alpha equals to 1. Right, this is from the Ceva's theorem. And we know AD cancels AD, BD cancels BD, DC cancels DC. So we got sine beta cosine alpha equals to cosine beta sine alpha, which can be rewritten as sine beta minus alpha equals to 0, which means beta minus alpha equals to n pi. So in this case, we know beta equals to alpha. So we prove that angle EDH equals to angle FDH. I would call this method as a straightforward method because we have the triangle here, we have the point of H, and we have 3 lines are concurrent. We can directly use the Ceva's theorem without adding any auxiliary lines. So it's pretty straightforward. If we look at this figure, and we have another method to do it. So I believe you are already familiar with the problem. So I'll just redraw the figure here. A, B, C, we have AD to be the altitude on BC and any point H on AD. We do the connection and we got BE, CF here. We want to prove that angle FDH equals to angle EDH, right? So for this case, we can extend, because we have the, again, we start from the Ceva's theorem, right? We can use Ceva's theorem on triangle ABC and point H. So we got AF divided by BF times FD divided by DC times CE divided by AE equals to 1. And because AD is perpendicular with BC, so we can draw a line through AD, through point A, that's in parallel with BC, right? Let's call this line as L. Then we know the angle DA, for example, this far away, we call it point Z. So DAZ equals to 90 degrees, right? So we got AD perpendicular with L. Then we extend CF, intersect L on point P. We extend BE. I'm not drawing it in a very good way. So let's call it Q. Oh, actually, sorry. My bad. Let's redraw it here. We shouldn't extend CF. We should extend DF because we want to find the ratio of AF to FB, right? So because we have BD to DC, so we want to find the BD to be correlated with BF. So that's why we want to extend the DF rather than CF. So let me redraw it here. A, B, C. Point H, D. Right, and there's lines here, yeah. So also far we don't know C. So the idea is what? Idea is we have this equation that is valid, and from AF to BF, we want to find some relation with BD. sorry, this should be BD divided by DC times C divided by E. Okay, yeah. So AF, we have the ratio of AF to BF, and we want to find it to be correlated with BD and DC, right? And also CE to EA. So that's why we want to extend the DF and the DE. Because once we already have a parallel line here, the L to BC, right? L in parallel with BC. So we extend the DF, intersect with L on point P, extend the DE, intersect with L on point Q. So we know that AF divided by BF equals to, because the triangle APF is similar to the triangle BDF, right? So AF to BF equals to AP to BD, right? So we have BD here. That's the thing we want because we want to cancel the BD. And we have this term here, and we also have CE to AE. CE to AE equals to CD to AQ. Right? We have CD here. That can cancel the CD. So we times them together, we got AP divided by BD times BD divided by DC times CD divided by AQ equals to 1, which means AP equals to AQ, right? Because AD equals to AD, AP equals to AQ, and angle PAD equals to angle QAD equals to 90 degrees, right? So triangle PDA and the triangle QDA are congruent, right? They are congruent. And from this, we got angle PDA equals to angle QDA. So this problem is not a difficult one, but it has several variants, can lead to be a very hard one. But the idea behind these are the same, that we can use the Ceva's theorem. We either find the area ratio and we transfer it to a sine angle to sine angle ratio, or we transfer it to some congruent triangles, right? The idea are the same. So based on this one, we will see some variants, but this is our very basic idea that we can do it from the area ratio, or we add some auxiliary lines to help us solve the problem. I hope you like this video. We'll see you in next ones. Thank you.